Hello and welcome. I'm going to do a walkthrough of the latest esports battle from the road to Las Vegas, which is a case called At the Races by James Curtis. So I'll spend a couple of minutes explaining it, and then I'm going to jump on in. Just to mention first, there are already two excellent walkthrough videos in this case. One that Harry Seiders did on I guess what I would call a relatively normal human way to solve the case, and one that Bo Rydobon did that's a little bit more kind of dynamic array heavy, although Harry did a reasonable amount of dynamic arrays as well. So I'm going to have it'll be a little bit similar if you've seen those, but I'm going to have a slightly more kind of Lambda focused approach for this one. All right, so let's dive on in. So we're looking at racing around a track. So we start here. Each square is 100 meters. So S is the start, N is a normal stretch of track, T is a turn, so just everywhere we go around a corner is a turn, and then the power-ups are you get a boost of speed on that square, and then for the next three after that. And then in some of the later rounds, we may or may not need to take a pit stop. So, the questions start off with simple things like if you're going at 100 meters per second, how long does it take you to get around the track? And it mentions in the instructions that the total number of units of the track is 72. And if you take the pit stop, because that cuts out some space, the total number of units of that is 65. So, here, for example, if you're going at 100 meters per second and you have to go around 72 squares, each of which is 100 meters, then obviously it takes you 72 seconds. And in general, you can kind of figure that out pretty quickly. Here, you're given your regular speed and your turning speed. So you have a different speed on turns here and here and here and here. So again, for that 100 meters. So again, you just need to figure out how far you're going at regular speed, how far you're going at turning speed, and then turn that into times for each and add them up. And then level 3, the power-up boost kicks in. So this is you go X% faster on the power-up square and the 3 squares after that. Important thing here, and I know this tripped a lot of people up, is there's a maximum speed even with the boost. So you're speed limited on the track to 200 meters per second. So here, for example, your base speed is 200 meters per second, so the power-up boost only makes a difference on the turn. It doesn't make any difference on a regular stretch. And then for level 4 and 5, you have a range, you're doing multiple laps, and you have a certain range that the car can go before it needs to make a pit stop. And so on a pit stop lap, it'll come through here, spend 10 seconds in this stretch, and then carry on around. So, and then level 5, you've got 100 different cars with different sets of stats for their speed, turning speed, how much of a boost they get, and the range they can go. And so for a certain number of laps and a certain set of 20 participating racers, you have to figure out which one is going to win. So I'm going to start at level 3 because levels 1 and 2 are kind of just special cases of that. And I'm going to write a lambda to solve this, and then we'll try and use that to solve level 4 and level 5. So I guess the first thing is, on the day I looked at this and I thought, okay, I need to kind of unravel this into a straight line. So, instead of going S, N, 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 I would go S and then a bunch of N's down here and then whatever, PU, and then carry on with whatever else. Not hugely time consuming to do that, especially if you use a little bit of like transpose or 2-row or other things to kind of flatten out straight stretches. But it turns out you don't really need to do that if you think through it. So what do you need to do? Well, you just need to think about how many regular speed squares there are, how many turn speed squares there are, how many power-up regular squares there are, and how many power-up turn squares there are. So the first thing that's going to be helpful is just to count how many of each of the 5 different types of track segment there are, which we can do just like this. And then what I would like to be able to say is normal, turn, power-up normal, and power-up turn. How many are there going to be for the regular, and we'll later need to know for the pit stop laps. So for regular normal turn, so the start counts as normal, and sorry, let me just, those here. Before I figure these out, I'm just going to also work out with no power-ups. So normal turns is just going to be the start square is normal speed, the normal track is normal speed, and the power-up is normal speed. And then the turns is just these 12. So then we just need to figure out how many of these are power-up. Well, lots of ways you can do this, but I think all the best ones are manual, or at least all the fastest ones are manual. So within this power-ups range, there's one turn. Within this power-ups range, there is one turn. Within this power-ups range, there's one turn. And for this one and for this one, there's no turn within range. So you got 3 power-up turns. And then how many power-up normals? Well, you could count them. So you've got, 1, 2, 3, 4, 5, 6, and so on. Or you can just say, well, every power-up affects itself and 3 other squares. So that's a total of 4 squares times 5 power-ups. You got the 5 here, gets you 20. So there's 20 power-up squares in total, minus the 3 that are turns, so you get 17 regulars. And then for this, you can just subtract off the ones that are powered up, and that's the ones that are regular. So that's how many squares at normal speed, at turning speed, at power-up normal speed, at power-up turning speed. So then we can come back and fill this bit in later on, but for now, let's do this. So we're going to say let, so we'll say let speed be this, let turning speed be this, and let power-up be this. Then what I want is, I basically want to line up the 4 speeds along with the 4 types. So I'm going to say hstack speed, turning speed, and then the boosted version of normal speed is going to be speed times 1 plus the power up, and then limit of that and 200. So we'll say min of this, comma, 200. And then exactly the same thing for the turning speed. So that outputs 4 different speeds there, and if I copy this up to the first row where we already mentioned the 200 is already the limit, so there's the speed and there's the turning speed, so that's good. So then if I have to go 4,300 meter squares at a speed of 75 meters per second, how long does that take me? So I'm just going to call this all speeds. So then what I'm interested in is all speeds, I'm interested in this lock times 100. So this is the number of squares, but each square is 100 meters, so this is the number of meters, then divided by all speeds. And that gives me the number of seconds spent on each piece. And if I copy that up here, that should check out to, yes, 41.7, so that's 42. And then, so here we needed to, sorry, not here, somewhere I mentioned, here we are, need to round your answer to the nearest second. So we just need to sum these up and round them. Also, because I'm referencing this, I would really be better off to give it a name. So let's call this units regular, and I'll call this units bit. So then in here, I'll just use units regular, and then this will be times, and then I want round of sum of times to 0 decimal places. And that's my 42. And then I can just take that. Well, anyway, I'm not going to take it and put it in here because what I want to do really is convert this into a lambda. So I've got, you can see I've set it up in such a way that I've got my kind of 3 variables here. I'm actually going to take this one out as a 4th variable because then I'll be able to use the same thing to figure out the time for a pit stop lap. So here I'm going to say lambda, and I'll just take all the variables out of here. And then I just have to delete each of the definitions. So I just want, what are the variables? So I want a speed, a turning speed, and a power up. And then I also want, I'll just call it units, which for now will be this. Sorry, again, I don't need to put in the definition, so I'll just put units there. And then the let defines all the other steps of the lambda. So then I just close that, and hopefully if I apply that to speed, turning speed, boost, and unit reg, that should give me my 42, and it does. I'm actually going to add in one more variable here because the other thing that you need for the pit stop is there's a fixed extra time, which is 10 seconds, I think. Somewhere here. Oh yeah, the pit stop always takes 10 seconds to go through. And 65 squares, yeah. Okay, so come down to where we were. Level 3, here we are. So we just put in one more variable here, which is, I'll just call it bit time. And so here that's going to be 0, and for a pit lap it'll be 10. Okay, so then now I have this lambda that I can take and make into lap time. Close. Actually, sorry, I want to take the round out of this because I want to round the output, but I don't want to round the calculation along the way. It's a little fix there. So put that in there. And so then the answers for level 3 should all be something like round lap time of this speed, turning speed, power up boost, and units regular. And 0. Round that to 0 decimal places. And then I think I mentioned levels 1 and 2 are just special cases. So here it's just a special case where you have no boost. So I don't even need to change anything. I can just leave that referencing an empty cell, but just make that 0. And then up here, same thing again, except this time I don't have a different turning speed. So I just have to use the regular speed as the turning speed. And that all checks out. Okay, so now I'll just clean these up. So now level 4, we're interested in, we've got again a speed, a turning speed, and a power up boost, but now we have a maximum range that we can travel. So here, for example, let's say here we've got a 20,000 meter maximum stint, and one lap is a total of 72 units, which is 7,200, which means you would not be able to make it around, you'd be able to make it around 2 full laps, you would not be able to make it around 3 full laps. So on the 3rd lap, you would have to come in here to the pit stop, go through there, take 10 seconds, and then carry on around. And then every 3 laps after that, you'd need to go back to the pit stop until you get to the end. So first things first, how many of each of these things is there for a pit stop? And I'm just going to do it as an adjustment. What do we change versus the regular? So first, there's some things that we take out. So we take out 1, 2, 3, 4, 5 normal squares and 2 turning squares in this kind of section of the thing that we trim off. And then the second thing is, we change what some squares are. So this goes from being a normal to being a turn. This goes from being a turn to being a normal, because here we're coming down here and we're turning, and here we're going straight through, not turning. Actually, sorry, I realized I got that wrong. So we do take out 5 normals, but actually this one is a powered up normal because this power up hits it. So it's actually -4 here and -1 there. And then we take out 1 powered up turn and 1 regular turn. So this is a -1 here and a -1 here. But then we turn this powered up normal into a powered up turn. So when we go back to -2 here, and add 1 powered up turn back, so make that +1. Whoops, not plus q, +1. And then also these two, these two, I've already had those 2 stop being powered up. So I think that's it. If I've got it right, then that should be my units pit. Now, have I, oh, whoops, I left the name up there. So let's just move that. Units pit can come down and be there. Okay, cool. So then I want my reg lap time and my pit lap time, and that will be lap time of this speed, this turning speed, this power up boost, units regular and 0, and then the exact same thing here, except it's now units pit, and the pit time is 10 seconds. That looks light. Did I forget to actually add the pit time in my formula after I added it as an option? I might have. Let's take this out and take a look. Yes, I absolutely did. So this should say sometimes plus pit time. So let's take that, put it back in, and hit close. And this should update, and it does. Okay, good. So now the key thing, the hardest part of level 4 is figuring out how many pit stops do you need. Now you can do this by, laying out a table with a number of rows equal to your number of laps and figuring out what happens to your remaining range after each turn. But there is a sort of neater way to do this. So first of all, we can figure out max laps without a pit stop. I'll just call it max without pit, and that is going to be this divided by 7,200, which is the size of a lap without a pit stop, and then round down, because so here this is you can go 2.777 laps. Well, if you can't make it to 3, then you can only do 2 laps. So this is going to be round down to 0. So that's if you have no pit stops. The most you can make it is 2 laps. So obviously that's not going to be enough, but it's possible that in some cases you would be able to. It looks like these lap numbers are mostly pretty big, but in theory at least it's possible you'd be able to make it without a pit stop. Then we'll consider the max with 1 pit stop. And what is that? Well, to get, and again it gives you this either here or in the question instructions. It tells you it's somewhere. It must be down here. In level 4, yes, it says, note the entrance to the pit stop is located 4,100 meters after the start. So, first question is, how many laps can you go around before the lap on which you have to go to the pit? So in other words, if your range was 5,000, then you'd have to go to the pit on the first lap. If your range was 20,000, like that first one, then you could do 2 full laps. That would be about 14,000, and then another 4,000 to get to the pit would be 18,000, so you'd be within range. So how many full laps can you complete? Well, it's going to be your total stint minus the 4,100 divided by 7,200. So in other words, your total stint minus the 4,100 is the range you need to get to the pit on your last lap. So then the rest of the range, you can use that to do some number of 7,200s, and we're going to just divide by 7,200 and round down to 0 again by the same logic as before. So that's oh, sorry, I didn't put an extra bracket there. So that's the number of laps you can do before, and then the number of laps you can do after is going to be, so if you got 4,100 steps to get to here, then you can just kind of count, or you can reference the instructions. The instructions say that the lap where you take a pit stop is 65 units long, so we should have 24 left, and that checks out, 24 there. So you got 2,400 after the pit. So then here it's going to be, again, round down, your range minus 2,400 divided by 7,200 to 0 decimal places. So that's how many laps you can complete after finishing off the lap you do your pit stop on, and then plus 1 for that lap itself. So here, if you make one, with no pit stops, you can only make it around 2 laps, but because the pit stop is somewhat in the middle of the lap, you can go sort of 2 full laps and a half-ish lap before the pit stop, and then a half and 2 full more laps after it. So with 1 pit stop, you can do 5. And then after that, you just need to know how many between pits. So in other words, if I can do 5 laps with 1 pit stop, then in between pit stops, I'm going to do, 1 pit stop size lap. In other words, from the exit of the pit stop back to the start of the pit stop, and then some number of full size laps until the next time I need to go into the pit stop. So here, that's going to be, so the pit stop is, it's 65 as opposed to 72. So you're saving 700 meters by being on the pit stop. So we're just going to be interested in the range plus 700 meters divided by the 7,200 rounded to 0 decimal places. So here in this case, we can go 2 laps between pit stops, because even with the extra 700 meters, the 700 meters that you save by 1 lap being a little shorter for going through the pit stop, you still don't have enough to make it around 3 laps. But in a couple of cases, that extra 700 meters does make the difference. So then finally, you just need to figure out, if you can do 5 laps with 1 pit stop, how many more pit stops do you need to get to 10? And that is going to be, so we're just going to say if max without pits is greater than or equal to 10, so I'm just going to call this is how many pit stops I need. So I'm going to say if the max without pits is greater than or equal to laps, then 0. Otherwise, it's going to be the total laps minus the number you can do with just one pit stop. So we need, and then just, it's possible that this will get greater than that, so we'll just take the max of that and 0. So this is the number of laps that you need to extend. So in other words, from this 5 to this 10, you need to add 5 laps, and you can add in multiples of 2. So how many multiples will you need to add? So here the 5 divided by 2, will give you 2.5. If you need to do more than 2, that means you're going to need to round up in this case. So round up this to 0 decimal places. So that's the number of extras you need to add, and just for the 5, you're doing 1 pit stop, so plus 1. So that is the number of pit stops that you need. And then finally, your time is going to be it's going to be 4 pit stop laps times your pit lap time plus total laps minus pit stop laps times your regular lap time. 443. That is not quite right. Oh man, what did I do wrong here? 442.57. That's terribly close, but it's not right. Have I done this wrong, maybe? I might need to be a little more careful here. So let me just kind of actually annotate what's going on here. So so here I had a power up normal. I end up with a power up turn. So that's minus a power up normal plus a power up turn. And here I had a power up normal, I lose it, so that's minus 1. Here I had a power up turn and I lose it, that's minus 1. And then here I had 3, 4 normals and I lose all of them, so that's minus 4. And then here I had 1 turn and I lose it, so that's minus 1. And then here I had a turn, which I lose, minus 1, and it turns into a normal, which is 1. So yes, actually something is not right here. So this should total to minus 3, that should total to minus 2. Okay. Okay, so now let's see if I check out. I do, so I think that means I'm right now, although hard to be totally confident when you've just hacked something like that. But anyway, that is the peril of doing something like that by hand. But, well, we'll soon find out if I'm right for this level at least. So we'll paste links in there. And those all check out. Good. So now the next challenge is going to be, can we squish all this into one big lambda? Because then, if I can, it'll be easier to solve level 5. Obviously, under pressure in the test, I don't know if writing it as a lambda is the way I'd go, but I'm trying to. Well, first, I'm just trying to show something a little different because a couple of people have already made videos about this one. And second, I'm trying to think not just about what do you want to learn for the test, but also what skills you want to learn for real life. So let's do this. I'm going to say, actually, I'm going to use a, well, let's start with this. So just widen this out a bit. So we say let speed be this, no, go away, be this, and turning speed be this, and power up be this, and range be this, and laps be this. Then whatever, then 1. And then let's start grabbing these formulas. So then let reg lap be this, where this becomes speed, and this becomes turning speed, and this becomes power up, and units reg and 0, yes. And then I'm going to do the same thing for a pit lap. Except now it's going to be units pit, and it's going to be 10 seconds. Okay, so next thing, I'll just put 1. So now I want my max without pit. Max without pit. And this is the range. And by the reason I keep putting in (1) at the end is just because it won't let me close a let with a series of pairs of definition and value. So there has to be an odd number of arguments, with the last argument being the output. So I'm just putting in 1 as a placeholder argument while I go back here to grab other formulas. So here, max 1 pit is going to be this. And again, just replace this with the range. And then between pits is this. Keep expanding that formula bar. Between pits is this. That's the range. (1), and we're almost there. So then the number of pits num pits is all this, where this is the max without pits. And here I'm just looking at the color here. So this color is this color. So this is my laps. And then this color is again that color. So this is my laps. And this color is this color down here. So that's my max with 1 pit. I call it max 1 pit. And this is my between pits. And again, I need to output something. And then finally, my time is this. Oh no, my time is this, and then rounding my time is a different matter. So time is this. So this is, get this out of the way, Q is my number of pits. And then this is my laps minus my num pits. And then this is my, what do I call it, pit lap speed. And this is my regular lap speed. And then output time. Okay, so then now I want to make a lambda here again. So we'll make it lambda of all these things. And we'll start the let on the next line. Actually, no, I won't. I want to start the let where I had it before. And so again, same deal. I'm just going to close that and open up, and I'll put the arguments here. So I'm just going to take the arguments out of here and put them down here. And this is the easiest way to convert a let into a lambda, which I've made longer, more detailed videos about at other times if you want to go check those out. Doesn't make for the most exciting viewing, I suspect, but what the heck? You get what you pay for when you pay nothing. Ha 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 ha. Okay, so that checks out. So now I've got my lambda, which is multi-lap time. So call this multi-lap time. Okay, so now I should be able to come over here and say round multi-lap time of this speed, this turning speed, this power up, this range, this many laps to 0 decimal places. Copy that down, and that works fine. And now we should be able to crack this last level relatively quickly. So here, we want to text split this by semicolon. That's going to give me my 20 racers. I'll just put them into rows for now. Into a column, or into rows, yes. Put a minus minus on that to make it numbers. So now I'm going to just say let racers be that. Then I want to map, and the function I want to apply is multi-lap time. So what do I want to map? Well, let's think about multi-lap time arguments. First argument is speed, so I want index on speed lock by racers, and then the second argument is index on turning speed lock by racers. And then the third argument, let's see, what is the third argument? It's the power up. So again, index on power up, lock by racers. And what's the fourth argument? The range and then the laps. So the range will vary and the laps is fixed for all of them. So index this, lock by racers. And then in theory, you could imagine that it might work if I just put in one value for laps, but I suspect that it might not like that because it's not the same size array as all the rest. So it might, sometimes when you provide a single value where an array is expected, it'll naturally broadcast that single value to the array. I don't know if that works with map. I guess we'll soon find out. It does not. So what we can do is we can say if racers is greater than 0, then that. And so that gives us our array of 20 times. So we'll just call this times. And then we want to know who wins. So that's going to be xlookup 0 in times, returning from racers with exact match or next larger item. And that is racer 58. And let's just check if we match in the example, and we do. Hooray. So then we can take all of this, put it over here, and fill down. And hooray, that all checks out. All right, so, and now we can tidy all this up because we don't need it anymore. And now we have it all working in nice single cell arrays. I'll spend 10 seconds on the bonuses if I can do them in 10 seconds, and otherwise we might just stop. All right, so the average speed, yeah, remember this was a pretty standalone one. So what's the average speed? At what average speed is the time taken to go around the track the same time as going around the track with a pit stop? So the key thing to notice here was what they had provided in the instructions, which is that it's 72 squares, so like 7,200 meters. Without the pit stop, it's 6,500 meters with the pit stop. So in other words, you save 700 meters by going in the pit stop, and you use 10 seconds. So for those two to be equal, 700 meters has to be equal to 10 seconds. You're going at 70 meters per second. Which racer has ridden the most laps across all the races in level 5? Okay, so I guess what I'm going to do is I'm going to map, because I'm going for succinctness here, map sequence, sequence 100. So for each of the numbers 1 to 100, I just want to figure out what is the total number of laps they've raced. In other words, the sum of these where they appear somewhere in here. And that is going to be lambda racer. I'm going to make it sum if, what do I want to do? If is number search. Now, the important thing about numbers is that they're not prefix free. So if I search for 1 in here, it'll match on 16. So what I'm going to search on is this and racer, and this, because they're delimited by semicolons. So I'm going to search for that in this range with, again, a semicolon added to the start and the finish to make sure that every pair is surrounded by them. So search for that in that. If that is a number, then we're adding up this. Close, close, close. So that will give me my list of 100 values. So just say let list be that sequence, then laps can be map, and then same as before, we're going to figure out who has the most. So we're going to xlookup some big number, let's just say 1,000,000, because nobody has raced 1,000,000 laps, in laps returning from list with exact match or next smaller item. And that checks out. And finally, for the racers in level 5, which racer has the greatest potential increase in speed from passing through a power-up in absolute meters per second? So here, we're just interested in which of these can get the biggest boost subject to the 200 meter per second limit. So I'm going to say I guess I'll do the same setup. Let list be sequence 100 and boost be this minus, actually, sorry, let's go boosted be this times 1 plus this, and then boost capped be if boosted is greater than 200, then 200, otherwise boosted. Then I guess the boost is going to be boosted capped minus the original speed, which is here. Then I want to XLOOKUP again, whatever. I guess none of the speeds are bigger than 200, so none of the boosts could possibly be bigger than 200. So look up 200 in boost, returning from list, exact match, or next smaller item. And that gives you 30. I will just kind of lodge my small protest here, which is that if you consider the boost that you can get on the turning speed, then actually this guy number 26 can get a bigger boost, because with the 20% boost, they get an extra 33, and that's still under the 200. So I think 26 is also a reasonable answer for this question. It's the answer I gave on the day, but 30 is the answer that gets marked correct. Anyway, that's all I got for today. I should mention Python has come to Excel. I am itching to get my hands on it, but I have not got my hands on it yet. I keep coming in here and typing equal py and finding nothing. But as soon as I get my hands on it, I'm going to be playing around in that sandbox quite a lot and trying to make you some videos about that. But for now, that's all I got. Thanks for watching, and see you next time.